Welcome to the Walton Pi. Today we are going to be talking about how we can match sequences to different exponential and linear functions. This is my 10th video covering AP Precalculus, so if this is helpful, please like and subscribe so you don't miss any of the other videos. So remember, an arithmetic sequence is any sequence whose successive terms have a common difference, or in other words, a constant rate of change. So when the common difference in the sequence is d and the zeroth term is a naught, we can write an is a0 plus dn, or alternatively, an is ak plus d times n minus k. Now, if this is a little confusing and you're not familiar with this, check out my previous video. I'm attaching a card up in the corner. This is going to get covered a lot more in depth there, so I'm not going to touch on it here. Okay. We have two equations for lines that are very similar to these sequences, namely y is y naught plus m times x, or y is y sub k plus m times x minus x sub k. The first is the standard form for a line, and the second one is the point-slope form of a line. Now, a geometric sequence is any sequence whose successive terms have a common ratio. So when the common ratio in the sequence is r and the zeroth term is g0, we can write gn is g0 times r to the n, or gn is g sub k times r to the n minus k. This is very similar to the forms of exponential functions that we've discussed previously, namely y equals y naught times b to the x, or y equals y sub k times b to the x minus k. This second form is just the exponential function with a known ratio and the point k y sub k. Now, there's an important difference between functions and sequences, and this lies in their domains. The domain of a sequence is all whole numbers, 0, 1, 2, 3, 4, and so on, while the domain of a function can be much more than that. It can be all real numbers. Additionally, in a geometric sequence, the common ratio can be any real number, while in exponential functions, the common ratio has to be 0 or positive. It cannot be negative. Okay? Thus, 1, negative 2, 4, negative 8, 16, negative 32, where the common ratio is negative 2, this is a sequence, a geometric sequence, with no corresponding exponential function. Okay? Subtle thing. The common ratio in sequences can be anything, while the common ratio in exponential functions has to be non-negative. Okay, let's talk about some properties. Over equal length intervals of the input, if the output values of a function are changing at a constant rate, then that function is linear. It's going to be a line. So over equal length intervals of the input, if the output values of a function are changing proportionally, then the function is exponential. If you check on equal length intervals, we are able to get that. Now, suppose that we know that the points 1, 4, and 336 lie on the linear function f of x. What is that function f of x? So, f of x is going to be some line, so it's mx plus b. That means we can plug in our 2 point values. So we know that f of 1 is 1m plus b, and f of 3 is 3m plus b, from just our equation of the line. And then we know that 4, because we know that we have the point 1, 4, 4 is going to be 1m plus b, and 36, because we have the point 336, 36 is equal to 3m plus b. So since 4 is m plus b, then that means that b is equal to 4 minus m. And since 36 is 3m plus b, we can replace the b with 4 minus m. So we get 3m plus 4 minus m, because that's our value for b, becomes 2m plus 4. So 32 is equal to 2m, which means that m is going to be 16. Then, since b is 4 minus m, we have b is 4 minus 16, so it's negative 12. So that means that f of x is 16x minus 12. That is going to be the linear function that passes through the point 1, 4 and 336. Now suppose that we know that the points 1, 4, and 336 lie on the arithmetic sequence an. What is that sequence? Okay, again, very similar to the line, we have an is d times n plus a0. We know that a1 is 1d plus a0, and a3 is going to be 3d plus a0. So that means that 4 is d plus a0, and 36 is 3d plus a0. And then very similar to what we did with the linear function, we can solve for what a0 is, and we can plug it into 36 equals 3d plus a0 to get 36 is 2d plus 4. So that means that 32 is 2D and D is going to be 16. So our arithmetic sequence, once we go through and solve for A0, is going to be AN is 16N minus 12. The arithmetic sequence is very, very similar to the linear function. Both of those get solved the same way and you end up with very, very similar things. Now, let's suppose that we know that the points 1, 4, and 336 lie on the exponential function f of x. What is that function f of x? Well, here our function is going to be a times b to the x. So we know that f of 1 is a times b to the 1, and f of 3 is a times b to the 3. So 4 is a times b, and 36 is a times b cubed. So since 4 is a times b, we can solve for a and get a equals 4 divided by b. And then since 36 is a times b cubed, we can replace a with 4 divided by b to get 36 is just 4b squared. So that means that 9 is b squared. Since the common ratio in exponential functions must be non-negative, we know that b is not negative 3, so our answer is just b equals 3. So since b is 3, we then have a is 4/3. So our function f of x is 4/3 times 4 to the x. Now, let's suppose that we know the points 1, 4, and 3, 6 lie on the geometric sequence Gn. What is that sequence? Well, Gn is G0 times r to the n, so G1 is G0 times r to the 1, and G3 is G0 times r to the 3. That means 4 is G0 times r, and 36 is G0 times r cubed. So since 4 is G0 times r, then G0 is 4 divided by r. So then when we plug that into 36 equals G0 times r cubed, we get 36 is 4r squared, so 9 is r squared, and r is plus or minus 3. So, depending on the problem, we need to use context to determine which is more likely, but both of these are valid answers. So, since r is plus or minus 3, we have G0 is plus or minus 4/3, so we either have the sequence Gn is 4/3 times 3 to the n, or Gn is negative 4/3 times negative 3 to the n. Both of these are valid geometric sequences that pass through the points 1, 4, and 336. I hope this was helpful in understanding geometric sequences and arithmetic sequences and their connections to linear and exponential functions. If it was, please like and subscribe, and if there's other things you would like to see me make a video on, please leave that in the comment section down below. I hope you have a great rest of your day, and good luck with all of your math.